let's insert a 9 into this tree. So to start with, we're going to say, is 9 less than 25? Yes. How's 9 compared to 20? It's less than, and greater than. So our 9 will go to the right of the 8. So now we have to say, well, is the parent a black node? If it was, we would just be done. It's not a black node. So we key off of the aunt node. So we have 2 reds in a row, which means we have to key off the aunt node. So the aunt in this case is a red node. So under those circumstances, we will recolor nodes 8, 10, and 15. So if you remember from our pseudocode there, we have to recolor the grandparent in these 2 colors. So in essence, we do that procedure where we move the color black down. So we've done that, which means we still have the same number of black nodes on any root to null path in this subtree, but we have to worry about, did we screw up the rest of the tree somehow? And we did. So in effect, we've got a violation here where we have 2 red nodes in a row. So again, when we have 2 red nodes in a row, we have to key off of the aunt node. So which one of these nodes is the aunt of 10? Well, in this case, we'll look at the parent, and then the grandparent, and then the grandparent's other child, which is the 30. So the 30 is the node that we'll key off of, and in this case, it's black. So the first time through, it was a red node, and all we had to do was recolor things. This time it's a black node, and when we have a black node, we have to do some rotations. So this is a left-left insertion. So if we look at the grandparent, the new node's to the left, and then to the left again. So that means we're going to do a right rotation around the grandparent to begin with. So that'll come down, the 20 will come up. So here is our newly rotated tree. And remember, 10 was the node we were treating as the newly inserted node, even though 9 was the one that we initially newly inserted. And we've done our rotation. So is this a valid red-black tree? Oh, well, we still have to do our recoloring. So for that, we are going to swap the colors of these 2 nodes. And so now after the recoloring, is this a valid red-black tree? Well, every node is red or black, so that's invariant 1. Invariant 2 was that the root was a black node. Invariant 3 was that there is no 2 red nodes in a row. And invariant 4 is that every root to null path has the same number of black nodes. So let's check that. 2, 2, 2, 2, 2. So every root to null path has 2 nodes. So all red-black tree invariants up are held, which means that's a valid red-black tree after our rotations. Okay, so here's our summary. Most binary search tree operations take the height, big O of the height of the tree in time. With an unbalanced tree, this can be as bad as big O of n. So if this is a very lopsided tree, we want to ensure that the height of the tree remains big O of log n. There are a number of different ways to do that. One of them is to implement a red-black tree, which implements tree balancing and has a guarantee on the height of the tree. This will require some extra work while inserting and deleting in the form of tree rotations, but they still are big O of log n amount of work. So the bottom line here is that as long as our tree is going to satisfy the red-black tree invariance, then we can assume optimal running time for red-black trees.